Well, thank you everyone for joining us today for our webinar on maximizing gateway math throughput for students who did not complete Algebra 2 in high school. I am Mallory Newell. I am the project lead for the Multiple Measures Assessment Project for the RP group and also the Director of Institutional Research and Planning at De Anza College. And I am joined here today by one of our other colleagues on the MAP project, Daisy Segovia. Daisy, did you want to introduce yourself?
Hello, everyone. I'm Daisy Segovia. I'm currently a research analyst at OCC, Orange Coast College, and I'm also a member of the MMAP group here at RP Group.
Thanks, Daisy. And then we are also joined by Craig Hayward, who will be running the webinar today. He's the Senior Research Analyst for the MAP project. And Craig, you want to give a little more intro about yourself?
Sure. Good afternoon, everybody. It's great to see you all here today. Craig Hayward, I'm the Dean of Institutional Effectiveness at Bakersfield College and have been working with the Multiple Measures Assessment Project, the MMAP project, for, 7 years now, Mallory, we've been developing
Yes,
that?
that's correct.
So this is a question that we are we've been really interested in, along with many of you for many years. So we're really happy to have a resource available for you to share with you today.
All right, and thank you. We just turned on the live transcription, so that is available if you would like. And we will be taking questions. You can enter your questions in chat, of course. We will go through the whole presentation and then leave time at the end for additional questions. And those that Daisy and I can answer as Craig's presenting, we will, but we'll mostly leave the majority of them for the end and leave time for those questions. So you can type them in or wait till the end and we can do some live answering. So we'll go ahead and get started with the webinar. So the agenda for today, for the hour that we have together, Craig, if you want to advance the slide. Thank you. So Craig's going to give a review of the new paper that is going to be, we're going to link to today so that you can read it after this webinar and give an overview of the framing of the questions that led the study and drove the research, a description of the study itself, including the methods and the sample that was used, the findings, and then, of course, time for discussion and Q&A at the end. So that's what we're going to be covering today. And I'll go ahead and turn it back over to Craig, and I'll go ahead and put in the chat the link to the full report.
Thanks, Mallory. And there's a bit.ly link up there. You can get the report on RP Group's website, rpgroup.org. And I'll walk you through it now. So definitely encourage you to read the full paper. We're going to start out by framing the context of the study. Why did we need to do this study? And essentially, it comes back to the California Community College Chancellor's Office default placement rules. These typically require direct placement of students into transferable college level math, but there are exceptions or exemptions to that rule. And the most common rule would be for a student who's pursuing a STEM program of study and who did not complete Algebra 2 while in high school. So in that case, it's open. Some colleges are placing those students into intermediate algebra at the community college, and some are placing them directly into transferable college level math. So that raises the intermediate algebra question. Does placement into intermediate algebra maximize the throughput of students who did not complete Algebra 2 while in high school relative to placing them directly into transferable college level math? So that's really the core question that I examine in this paper and in this study. A couple of notes here just on nomenclature. Algebra 2 and intermediate algebra are really essentially the same class or the same course. However, just for clarity, I'm going to use Algebra 2 to refer to the high school curriculum, and intermediate algebra to refer to the community college curriculum. Additionally, Algebra 2 is an umbrella term, and it includes similarly named classes that might be called, they might even be called intermediate algebra at the high school. Importantly, also integrated math 3 is considered an equivalent to Algebra 2. And the same goes in terms of naming at the community college level. Not every intermediate algebra class at the community college level is actually called intermediate algebra. So those are all included in here regardless of naming conventions. Another note, and it's right in the title of the paper, this word throughput is a relatively new metric developed as part and really kind of gets popularized by the Multiple Measures Assessment Project research team. And it's a way of conceptualizing the outcome of students who begin at a certain point through a key gateway course. So it's essentially the percentage of a given cohort of students who start in a particular time and defining that cohort, and the percentage of that group that completes the designated gateway course. In this case, we're talking about transferable college level math course within a designated time frame. The designated time frame under AB 705 being within 1 year of the initial math attempt. So that's what throughput is. This dense slide of words are the research questions that are addressed in the paper, but I'm going to kind of skip over that and get to a simplified version. So essentially the same thing. And these are the questions that are going to frame the presentation today. We'll kind of work our way through these questions. What percentage of incoming community college students have not completed Algebra 2 while in high school? This is a common question. What is the throughput of students who have not completed Algebra 2 in high school if they begin in intermediate algebra at the community college versus that gateway transferable college level math course, their initial college level math course if they're in a STEM program? And speaking of students in a STEM program, we're particularly interested in those students, given that they're at the core of the exception to the Chancellor's Office guidelines or default rules as they're known. And so those students who are pursuing a STEM program study, do they attain higher throughput rates if they start in intermediate algebra or transferable college math? And importantly, we find, does high school GPA factor into the picture, and how does it affect our overall understanding of this relationship? So to address this, we have essentially two samples. So one study, two samples. The first sample was a smaller sample of students with complete high school records. So they had a cumulative GPA for every year that they were in high school: 9th grade, 10th grade, 11th grade, 12th grade. And we used that sample to identify a minimum set of information necessary to determine if the student had completed Algebra 2 in high school. And then the second expanded sample, which had nearly 3 times as many students, giving us more power to explore those subsequent questions, was used to answer those remaining research questions. So in order to be included in sample 1, or who is included in sample 1, they're students for whom we had a high school GPA, a cumulative GPA for each high school grade level. And I call that a complete high school record. And there were math course codes and descriptions for at least 2 grade levels. Most had 3, but we expanded it to 2. And as you'll see, many students do not take math in every grade level that they are in high school. So 2 was considered sufficient for determining their math enrollment. And then all of these students would then also have a subsequent math enrollment at the community college. So that's sample 1. And with sample 1, we created this figure, this analysis, which is called the Sankey diagram. And it basically shows the flow of students through their math coursework over the 4 years of high school. Starting from the left-hand side of the screen, we have 9th grade math enrollments, and the length of the bar shows the relative size or the relative number of students that are enrolled in each of those courses. And for instance, at the top left, you'll see Algebra 109, which means that in 9th grade, Algebra 1 is represented by that long blue bar, indicating it's the most popular enrollment option, the most common enrollment option for students in 9th grade in California high schools. Also point out the yellow bar in the middle on the left-hand side has no math. So that means that a group of students for whom there were no math course records available, either because they were skipping math in that term, or it was missing data in the administrative system for some reason. And then the gray lines show the flow of students from one course to another. So Algebra 109 in the upper left, a big gray flow goes directly into Geometry 10, and then from 10th grade geometry into taking Algebra 2 in 11th grade. And then the biggest gray outflow from Algebra 2 in 11th grade is to essentially taking no math at all in the 12th grade. And that was the most common pattern among high school students, but by no means was it a dominant pattern, because there are so many different variations of patterns, as you can see here. And this is essentially all of the students from sample 1. 99.5% of the students in sample 1 were included. There were some extremely uncommon patterns that were excluded just for legibility of the diagram, but a very, very small number. So that allowed us to do a qualitative analysis and quantitative analysis of course taking of students in high school, which was an important step to building the sample that was going to allow us to evaluate the rest of our research questions. So the rules that we derive for inclusion in sample 2 is there must be at least one cumulative high school GPA recorded for at least one grade level. And part of the reasoning we only require one grade level is there's a very high level of correlation amongst cumulative GPA from year to year. The lowest level of correlation being 0.84 for 9th grade cumulative GPA to 12th grade cumulative GPA. And the remaining correlations all being in the 0.9 or higher range. So essentially knowing one cumulative GPA point gives you a very good indicator of that student's overall cumulative GPA. Math course enrollment record for at least 11th grade or 12th grade. So we're able to pare back the amount of information required greatly, which allowed us to expand the sample size. However, there's a caveat to that, that last rule that I stated. The student's highest math class in 11th or 12th grade was geometry. They must also have a prior math class on record, because there is a pattern by which students take Algebra 1, Algebra 2, and then take geometry. So if geometry is showing us their highest math in 12th grade, we would need to know what did they take in 11th grade? Were they taking Algebra 2? Because technically Algebra 2 we would consider to be quote unquote higher than geometry. And then of course these students would need to also show a community college math enrollment. So that's the criteria to be in sample 2. Here are the descriptive statistics. I'm not going to read this table to you. It's included here for posterity. It's also of course in the full paper. Essentially the samples were very comparable in terms of GPA, gender balance. There were some small differences, the largest difference being the number of high school math courses recorded, but that was intentional as we expanded the sample to include sort of students with less complete information, but sufficient information to determine highest math class taken. So a little bit about the findings. I already mentioned that Algebra 1 to geometry to Algebra 2 to no math was the most common course taking pattern, but by no means was it a dominant pattern. It only represented about 8% of students. So they're, one of the take homes is that course taking patterns are highly variable. Looking at 12th grade, typical math enrollments for those who were enrolling in math were statistics or Algebra 2, but about 37% of students enrolled in no math at all in 12th grade. And this is consonant with other research, such as Finkelstein et al. And Asim et al., who looked at a larger group of students. They found less math skipping in 12th grade, but they were also including students who were going to UC and CSU, and students who are higher achieving tended to abstain from math less frequently. So they're finding about a quarter to a third of California students taking no math in 12th grade are finding a little bit higher, but probably understandable given our sample selection. So overall, bottom line, 65% of sample 1 and 62% of sample 2 had completed Algebra 2. So that positions us to use sample 2 to delve into our subsequent research questions regarding students who did or did not complete Algebra 2 in high school. What is the throughput rate when they enroll directly in transferable college level math, whether that's SLAM, statistics, liberal arts math, or BSTEM, business, science, technology, engineering math pathways at the community college. And also, we're going to take a kind of a sub-research question: how do historical patterns vary, given that fall 19 was the term and the year 1920, which AB 705 legislation went into effect. Excuse me, let me clear my throat. We've got a very interesting finding when we compare the historical pre-AB 705 cohort to the post-AB 705 cohort. And what we see going on here is that overall throughput rate is increasing. And that's for students with no Algebra 2 in high school, it goes from 20% to 28%. And for students with Algebra 2 in high school, it goes from 35% to 47% overall. But interestingly, the opposite is happening for the subgroups that we're looking at. So for students who enrolled in intermediate algebra and had no Algebra 2 in high school, throughput rate was 11% prior to AB 705, and then only 8% post AB 705. Whereas if they had Algebra 2 in high school, this is the gray bar in the second set of columns on the left-hand chart, it's 18% throughput rate. And then post AB 705, the second set of columns in the right-hand figure, it's 13%. So that's declining, and that pattern holds for students who are starting in SLAM, transferable college level math, or BSTEM, transferable college level math. So this is what is known as a Simpson's paradox, where the trend for the overall population doesn't hold true amongst the subcomponents of the population. So how can that be? And essentially, it's because there's a huge movement of students from a lower throughput entry point of intermediate algebra into transferable algebra, into transferable college level math, and which could be transferable college algebra, but not necessarily. That movement increases the overall throughput rate for the entire cohort. So it's an interesting situation in which overall throughput is increasing, but depending on your perspective and where you sit, and what data you're looking at, and maybe if you're in a classroom versus looking at administrative data sets like this, you may have a different experience or perspective about what's going on. So the key findings from research question 2 and 2.1 are that overall, only 8% of those beginning in intermediate algebra completed any transferable math within 1 year. So that's an 8% throughput rate. Those who began in a transferable college level statistics or liberal arts math achieved a 37% throughput rate, and those who directly entered transferable BSTEM achieved a 30% throughput rate. The overall throughput rate increased for the post-AB 705 cohort relative to prior years, and the presence of that Simpson's paradox may contribute to different perspectives on the impact of AB 705. So moving on to research question 3, what is the effect of different levels of high school math course attainment on math throughput after controlling for variations in high school GPA? This is an important question because there is a strong confound of a high school GPA with highest math course completed in high school. As you can see in this figure here on the screen now, students with higher levels of math attainment on the right-hand side of the figure have higher average GPAs. Those are the numbers. So if students who've completed calculus in high school have on average a 3.4 and then attend community college and enroll in community college math. So this is our, our sample we're talking about, have on average a 3.45 high school GPA, whereas students, say, who only completed Algebra 2 in high school have on average a 2.85 GPA, and so on and so forth. So it's important to also control for the impact of GPA as well as high. So what are the independent effects of these two important variables? Because we understand that both of these things are likely related to math throughput at the community college. So to evaluate that question, I developed a logistic regression, a multivariate model in which we included high school GPA, the entrance point of the math pathway, whether it was transferable college level math or not. And then the highest high school math is prior to Algebra 2, or the highest high school math is subsequent to Algebra 2. So this is breaking the figure here, all of the different possible highest levels of math down into 3 groups, essentially math that's less than Algebra 2, math that's exactly equal to Algebra 2, and math that's higher than Algebra 2. And the way it works for the Algebra 2 factors here is that we leave out Algebra 2, and that's the comparison group. So we will interpret the effect of highest high school math in relation to the group of students who complete exactly Algebra 2 in high school. So I'll walk you through this. In bold is the most kind of pronounced effect in the model, which is the entry point into the math sequence at the community college. This is a very strong effect, the odds ratio 6.67, 1, and significant, statistically significant. And what it means is that students who enter transferable college level math, their odds of completing gateway math within 1 year are 6.7 times higher than students who enter at intermediate algebra. High school GPA is also a very, very strong predictor. So these are both present in the model as strong statistically significant predictors. And the number's a little bit lower, but this number is for each point change in GPA. So going from a 2.0 to a 3.0, a student with a 3.0 GPA, the odds of their completing transferable college level math within 1 year of their initial attempt are 3.43 times higher than a student with a 2.0 GPA. And so that can stack. So if you go 2 to 4, it would be twice. It would be 6.86 times more likely for a student with a 4.0 to complete than a student with a 2.0. And then the highest high school math is important. If you've completed less than Algebra 2, the odds ratio is less than 1, which means that these students are statistically significantly less likely to complete relative to students who less likely to complete their gateway math at the community college than students who had completed Algebra 2 in high school. And if they had completed above Algebra 2, then they're 1.48 times their odds of completing gateway transferable math at the college are 1.48 times greater than students who only completed Algebra 2. So the multivariate model sort of backs up what we're seeing in the earlier descriptive statistics, where we saw the Simpson's paradox. So the key finding there, I've already reviewed that. On to our last research question. So among students who've declared a STEM program of study who have not completed Algebra 2 in high school, and this is the exception group or the exemption group that we're particularly interested in, which placement, transferable college level math or intermediate algebra, is going to maximize their probability of completing a STEM pathway math class at the community college? So what we see is a clear pattern that corresponds with the findings of the earlier research questions. So Algebra 2 students who have completed exactly Algebra 2, if they enter into a transferable college level math class, their odds of completing that gateway math within 1 year are 58%, relative to 21% for those who would be assigned to intermediate algebra. That's sort of a mid-range. There's a lower set of throughput rates for students who highest level of math attainment in high school is less than Algebra 2, and then a much higher group of throughput rates for those who have completed greater than Algebra 2 in high school. And consistently, I mean, it's the throughput rates are higher for the more math that a student completes in high school. You tend to see higher rates in general, but there's always this pattern of the entry point into math at the community college making a very large difference in throughput rate. So always an edge given to the students who are able to start directly in transferable college level math. So to summarize, the students who had not completed Algebra 2 in high school were much more likely to achieve math throughput if they began in transferable college level math than if they began in intermediate algebra. And essentially we see that those students break down into 3 tiers. So those with less than Algebra 2 in high school, those with exactly Algebra 2 in high school, and those with greater than Algebra 2 in high school, having around a 70% to 80% throughput rate at the highest end. So how could this be? This really, I think, runs contrary to many people's intuition, a lot of thought and work that's been given to developmental education, an understanding of the structure of the curriculum, the math curriculum, and how it builds upon itself. So how could it be that direct entry into transferable college level math is so clearly superior in terms of throughput to entry into intermediate algebra? Well, that may make sense for students who've already completed intermediate algebra or Algebra 2 at the high school or higher, although given the way assessment and placement has worked in the system over the years, many of those students who have completed those higher levels of math nonetheless are placed into intermediate algebra or even lower when they enter the community college. Not anymore post AB 705. So now the question is really, does intermediate algebra, is that the best entry point to help students sort of get up to speed and be successful? And clearly it's not, but the head scratcher perhaps is why? Why is that the case? Why are we not seeing that intermediate algebra does boost students' throughput? And probably the biggest reason and the biggest issue is the problem of attrition. At least it's the one that's, I'd say, easiest and clearest to measure in the data. We see that when students enter intermediate algebra, there are issues of persistence in the sequence and issues of retention and persistence at the college. So if you can think of it this way, that you might have just one shot with this student to get them through math with some of our students. And if that shot isn't college level, then we may just lose them, and then that's the end of their progress. So there's also the problem of underplacement, which I was just referring to, where students who've already completed curriculum at the high school are repeating that course or taking even a lower level course when they come to the community college, which can lead to a problem with engagement or discouragement. And we see this in qualitative research projects that have engaged with students regarding their experience around placement and a sense of being misplaced. There's a renewal of interest in this work with Tatiana Melguizo at USC and Fred No also at USC, doing some really good work recently looking at underplacement and misalignment of curriculum from high school to community college. And that, unfortunately is more common, they find, with students of color to experience misalignment in placement. A couple of other possibilities are misalignment of the DevEd curriculum with college level curriculum. So when a student is taking, for instance, intermediate algebra, if they're not a STEM major, that may be in a sense overkill to prepare them for a success in a statistics class, where there's not a lot of overlap between the material that's covered in Algebra 2 and the math content of a statistics class, which will transfer to the university and satisfy that student's math requirement. And then that's related to the question of misalignment of math pathway with the program of study. So we do see post AB 705 a large shift of students into more statistics-based or SLAM math pathways. And so that's an indication of greater alignment of math curriculum and math course taking with program of study. So all of these issues are being ameliorated or addressed to some extent by AB 705 implementation. So another way to think about this is to think about it in terms of structural and instructional efforts to improve student math attainment, completion, and progress in the sequence. And when we're talking about throughput, we're often talking about these sort of big moves with structural alignment from high school to the community college and improvement of assessment and placement systems to address the issues on the previous slide, such as underplacement. Additionally, under structural, I would say the development of curriculum that is co-requisite developmental education or concurrent developmental education, which addresses that attrition issue. So it's not that developmental education per se is an issue, or a problem. It's a big problem is the attrition that's created by multi-term sequences of developmental ed, which may reduce student engagement and facilitate student dropout and lack of persistence. So another structural move is the reduction in developmental education units that do not generate momentum towards degree completion or transfer. So that's an important factor. It's a structural factor. The college level placement systems have had a major overhaul in the past few years, and this is reducing underplacement or repetition of courses that are already completed in the high school. And then, of course, the program-specific math pathways and the growth of the statistics liberal arts math pathway for students who are not business STEM majors who need the kind of more intensive calculus-oriented math pathway. Those are again kind of, we can put those in a bucket, kind of big structural moves. A lot of work been done there. A lot of work also going on in the instructional, and I just want to give a nod to this. This is not necessarily the focus of the current research, but this is also happening concurrent with the big structural changes. We're seeing a lot of focus, a lot of professional development around, for instance, support for students' affective and basic needs. So often the reason a student doesn't succeed or persist is not due to cognitive or academic reasons per se. It has to do with their life circumstances and issues that can be addressed by holistic wraparound services and addressing basic needs such as housing security and food security. Humanized pedagogy is another sort of move in the instructional space where you can think about this as the teacher facilitating learning versus policing learning. Flipped classrooms are an example where learning, you kind of take the sage on the stage model and put the students at the center of the learning activity, giving them center stage, and the teacher is the facilitator of the learning in that context. And just-in-time support is another example of instructional moves that are being made that are more on the pedagogical or instructional side and less on these sort of big structural sides. Heading into, let me do a quick time check here. Doing all right. Heading into the wrap up here, wanted to cover the types of concurrent or co-requisite remediation that are commonly observed out there. So we have, I put together all sort of paired classes co-requisite remediation in one group. So, but this is paired classes, so the student needs to enroll into 2 separate classes, and that may or may not be with the same instructor in both. So that's kind of a flavor, a different flavor of paired classes. And then as a sub-bullet under there, particularly noting the accelerated learning program or OUT model, which I think originally started at Baltimore Community College, Baltimore, I'm saying that right, Community College of Baltimore or Baltimore Community College, and is very big in New York. And this mixes developmental education assigned students and college level assigned students in the base college level math class or English class, and also present for English. And then just the dev ed assigned students also attend a co-requisite class. So it's kind of a very specific way of doing paired classes, and it also includes the wraparound holistic support very intentionally. So that's sort of a super co-requisite remediation approach, very I was going to say enhanced one, but then I don't want to say that because that's the next, but it's a very strong one with very strong results that are in the literature. So the next method of co-requisite remediation is, sometimes we call this enhanced classes or extended classes. So these are additional time or units added to the base class with the same instructor. And typically it would be students who are have been flagged as needing additional support, who would be in that class. So sort of 100% dev ed assigned students. In the default placement rules in California, for instance, these might be students with a range of GPAs from say 2.3 to 3.0. And we also see in Texas the non-course based option, although since the non-course based option is unit bearing, it might be it's a little, I'm a little confused by that one. It seems a little a bit of a misnomer, but the non-course based option is essentially an intensive pre-class dev ed experience. So we see also those are called sometimes math jams or summer intensive. And it's a way to sort of ramp up student preparation for success in the college level course. And that's popular in Texas. And then technology mediated models. So this would be an independent lab with computer adapted models. There isn't necessarily that same instructor facilitating that lab. So the student is sort of doing independent learning through technology and adaptive models to supplement their progress in a just-in-time way in the main college credit bearing class that they're enrolled in. So a lot of different options and some questions around which of those models are most successful with students. So we'll talk about that in the further research. First, on the basis of this paper and the findings, we have some recommendations that the level of support be gauged to be aware of the student's highest level of math attainment in high school. So if their high school math profile includes successful completion of a course subsequent to Algebra 2, these are the students in the 70 to 80% default kind of throughput rate. They have the highest average throughput rate. Place them directly into transferable college level math. Additional support is optional depending on how that works at your college. It's not necessarily seen as extremely necessary beyond sort of the typical support you would provide to your students. In the mid range would be students who complete exactly Algebra 2 in high school, but not higher. Place those students as well into transferable college level math. Consider giving them a moderate level of additional support as their throughput rates are not as high as students who've completed beyond Algebra 2. All things being equal, all other things being equal. And then certainly students who have completed less than Algebra 2 in high school do have the lowest average throughput rate, although it's much higher if they begin at the transferable college level math placement. So place those students into transferable college level math, but consider giving them the highest level of support, including holistic support for non-academic issues. And so those would be the recommendations coming out of this paper. Of course, this is just one paper and one data set, and every analysis and every research project has its limitations. So for instance, we were not able to assess the level of extracurricular math instruction that students had, if they were engaging in things outside of the high school curriculum, Khan Academy, things like that. We wouldn't have that in our data set. Also, in sample 2, perhaps students who are missing more math taking data may be systematically different really than those included in the study. So we're really talking about students who weren't in the study because they didn't have enough math taking data. So they may be coming from high schools or parts of the state that are systematically different than those that were in the study. Just given the size of the sample, 1.2 million students is a bit of a hedge against that, but that, that is something that is a possible limitation. Also, we equated integrated math courses with traditional counterparts. We did take a look at that. It seems to be reasonable to do, but just something to note. Integrated Math 3 was equated with Algebra 2. Integrated Math 1 was equated with Algebra 1, and Integrated Math Integrated Math 1 was equated with Algebra 1. Integrated Math 2 was equated with geometry. Of course, COVID-19 hit in March 2020. So towards the end of the 1920 academic year, the first year that AB 705 went into effect. So that is a concern. I did look at the pass rates of students in math classes. In particular, the pass rates in spring 2020 actually were higher than pass rates in math in spring 2019, even when you include EWs as non-successful attempts. So it didn't seem to have the concern is that it might be depressing throughput rates, didn't seem to necessarily have that impact. But nonetheless, we all know COVID-19 is going to have 1920 data have a big asterisk next to it for the many years to come, probably, well, forever, really. So it was a very exceptional year. We will want to replicate the findings of 1920 with future years' data. And then finally, students in this sample represent those students who they're high school students in California who go on to California Community College. So university matriculants, students who don't go on to post-secondary may have different profiles and outcomes. So some of the limitations, a lot of ideas for further research. I think probably the most important one to call out based on feedback from the Academic Senate for California Community Colleges think we've heard that a very keen interest in understanding, what are the downstream effects of changes in access to these key gateway math classes. So we're seeing throughput, one-year throughput rates going up. What about the subsequent math classes for STEM students? Because of course, that initial transferable college level math class is really just the beginning of the math journey for a student on the STEM pathway. So they have multiple math classes to make it through. So we'll be watching that data point with great interest as more data accrues, and we can kind of see how students are progressing in their future coursework. I'm going to kind of we can circle back to this, but I think we want to get to, I'm seeing that there are a number of questions, Mallory, and you've been probably answering some of those in chat. I've been ignoring them so that I can get through the presentation, which I've done, and we have some time left to get into the Q&A. So why don't we do that?
Very well done. Thank you, Craig. There's a lot of information to cover, and we have about 14 minutes for questions. A lot of the questions that came in were answered as you went. Daisy and I were trying to answer many of them that we could. And we have questions in the chat and in the question and answer. There was a couple of questions that came in. Let me just point to some. So there were two questions around if the students had IEPs or were DSPS. And I did link to this a prior study that RP Group has done that still found that throughput is higher for DSPS students if they are put into transfer level opposed to pre-transfer level courses. And that is across the board for all the students groups that we've been able to look at. So I did link to that there. So that came up twice.
I would say that's also a really important question for further research. And so in the full paper, we refer to the other work around the equity question for different groups and the certainly the closing of gaps in terms of access and the improving throughput rates for all groups that have been identified, including DSPS students. We don't have good access to IEP data from high school, unfortunately, so that's not clear amongst our sample, but certainly we've said in the past that these are sort of general default rules, and that there can always be an exception made for students with different kind of background factors. But DSPS is one that we've looked at very carefully, and that is not one we don't see negative impacts on students with DSPS. So I wouldn't want them to be sort of exempted from the benefits of higher throughput.
Thanks. So then there's a question from an anonymous attendee. Since intermediate algebra is the level of associate's degree, is the recommendation to have all students, regardless of their ed goal, certificate AA, et cetera, to enroll in a transfer level math course to satisfy it?
That's a good question, because that's another exemption to the default rules of placement directly into transferable college level math. So if a student has an ed goal that's a certificate or perhaps an associate's degree, a local associate's degree that doesn't require transferable math, they may have a more appropriate math curriculum for that program available to them. So it's not in any way meant to override those types of considerations and that kind of curriculum development that's been done for specific programs. That those should still stand, those are fine. On the other hand, consider that for instance, a statistics class, which shows extremely high levels of throughput, even for students with lower levels of math attainment and lower levels of high school GPA, still have very, very relatively high throughput rates in statistics class. If that class can function, and it does function to meet the degree requirements for most local associate's degrees, if it also makes sense in terms of curriculum and program, that could also be a viable option in addition to a non-transferable. Because of course, if the student completes a transferable class and then later decides, even though they've completed a local associate's degree, that they would like to transfer, they have that in place. So there's certainly, I think, a lot of factors to consider around what math pathway is the programmatically appropriate math for that student. So we wouldn't want to be sort of monolithic in recommending only one approach for all students, regardless of their ed goal or program.
Great, thank you. Okay, and then another question from another anonymous attendee. Did all students in this study take only intermediate algebra or a transfer class on the STEM path, or did some of the students take a transferable class on the SLAM path?
Well, some definitely took the SLAM path, but when we looked at the STEM students, we're looking at for STEM path completion or STEM math completion, if that makes sense. So in some of the questions, we wanted to compare SLAM completion to BSTEM completion, but in question 4, when we're looking specifically at STEM students, we're looking specifically at STEM math.
Great, thank you. So there's a question about the starting point of the sample. Were you beginning with high school transcripts and pick out those that meet the selection criteria, or starting with community college transcripts and pick out those that meet the selection criteria?
I'm muted. I apologize. Could you say that question more time, Mallory?
Yeah, so for the selection criteria, were you beginning with students' high school transcripts and picking out those that meet the selection criteria, or starting with community college transcripts and picking out those that meet the selection criteria?
Mallory, what would you say? How would you answer that question? I think it's both, right? I don't think.
Well, I would say we weren't picking out particular students. We had our research questions, and then students fell into the different categories.
Well, I think we looked at both. So we have in the sort of the kind of the original big pool of data, students who have high school transcript information. I think I think it would be fair to say that the primary filter is community college enrollment. If they don't have a community college math enrollment, then they wouldn't be included, but they do need both. So I don't know if that answers the question. I might not be understanding it fully.
Yeah, and if you wanted to rephrase that question, we could see if we could attack it a different way. But so there is a question from Ryan. Is stats completion being included in STEM math or only calculus-oriented STEM courses? This is still unclear to him.
So college algebra is considered a STEM course in this sort of categorization that we have here. So it's only SLAM courses are statistics and liberal arts math courses, and we have a very kind of fine-grained analysis across the system of what falls into what category. So college algebra, trig, pre-calc, those are your typical initial kind of STEM or BSTEM pathway math classes. And if a student starts higher, they would be like, we do have students obviously that started Calc 1, that would also count. They're not, those higher level math classes are not excluded.
Yeah, and there's quite a few questions that come in around the effects of COVID and the time frame of the data. And I know you touched on that a little bit in the caveats, but maybe just going over that just really quickly about what the time frame was and how that may apply now with the decrease in enrollment in online learning.
Right. So particularly with the research question 2, where we're looking at the historical impacts, there's this sort of there's this opening for a history bias to enter the question or enter the equation or picture, which is because obviously COVID-19 pandemic hit really hard in the middle of March 2020. Colleges all around the state shifted to online, closed down their physical campuses. There was a great expansion in the number of students taking EW grades. Those EW grades, when there was a question whether those should be included as non-successful attempts, which we did, because that is more congruent with including, say, withdrawals, other withdrawals as a non-successful attempt. And those students did not, in fact, successfully complete that math class. So there was a concern that that would depress the throughput rates, or at least depress the success rates in the spring math courses. But when you look at the statewide numbers on pass rates in math classes in spring 2020, including EWs as non-successes, they're 3 points higher in spring 2020 than they were in spring 2019. So it did not seem to have a depressive effect on throughput. But again, obviously other things, there are a lot of things that happened because of and concurrent with the COVID-19 pandemic. So I think we would want to replicate these findings in, say, the future years. I mean, 2021 also a bit of a weird year in terms of enrollment patterns and whatnot, but this is the current reality that we're living in. And this is how the student progression and completion is showing up in these challenging circumstances.
Great, thank you. And this one came up too. There's a little bit of a discussion around how students got into the cohort. So the question is, if a student opts to not take math in their first semester, would they not be included in the study? Are you only looking at those students who took math in their first semester, and then they wouldn't be included otherwise?
Yeah, no, so that's kind of, yeah, that's understandable because that's the student-centered funding formula approach to calculating throughput for for funding purposes. But the MAP approach and the AB 705 approach is to look at the first attempt in the sequence, regardless of when it happens. So it's not necessarily just first-time freshmen taking it in their first term. It's whenever they're taking their first math class.
Thanks. And then any distinction between the modality face-to-face and DE at this point?
No, we don't. We haven't looked at modality. I think that's if that is not on this slide of further research questions, it should be. I think it's something we're all really interested in and looking at as institutional researchers right now. All the cool variations in modality. So I look forward to hearing from everyone else who's doing that research, how that's starting to show up. So many interesting variants in modality, synchronous online, asynchronous online, hybrid, face-to-face, and then of course we have all of the variations of Corequisite and concurrent developmental support. So yeah, lots to keep us busy over the coming years.
And then a question for Maria, if quantitative reasoning courses such as Psych Stats, Soc Stats was included.
Quantitative reasoning courses such as what?
Psych Stats and Soc Stats. Yes,
yeah, so those are included. There was a lot of work done to get all of those, we call them non-math math classes, if that makes sense, get those included as in the SLAM pathway.
All right, and then just one last question, maybe really quickly, the last one. How was the data gathered? Maybe just a little bit more how we get the data and who's included in that.
So our partners in this work are, of course, the California Community College Chancellor's Office that makes this work possible. And the Ed Results Partnership is sort of our data workhorse. And they provide MIS data matched with the CalPass Plus high school transcript level data for the research project. So that's the data source for the intersegmental data set that we're working with here.
All right, so we are at the 1 o'clock hour. We want to thank everyone for attending on a Wednesday afternoon. We will post the recording and the presentation on the RP Group Multiple Measures Assessment Project website. And we can also send it out to the RP Group listserv once that gets posted along with the release of the report. And you can also, reach out to any of us with any questions that you may have. I see that Daisy's put the links in there. So thank you so much. And thank you, Craig, for this amazing research and for sharing it with all of us today.
My pleasure. Thank you all.